So 9C, you're going to be delving into exponential modeling, which isn't quite as intuitive as linear, but it's still not too bad. Okay, so remember we said exponential modeling is when you're increasing by a percentage rather than a specific amount. So for example, let's say we look at a town with an initial population of 10,000, and you're growing at a rate of 20% per year. So it's 20% of whatever the previous one is. So the amount that you're going to add on is going to be different every time. So the initial population is 10,000, 20% growth rate. That means that the next population is going to be 20% more than, or 120% of. Remember, we have talked about this already. So 120% of is going to be 1.2 times the initial population. So we take our initial and we multiply by 1.2 to get 12,000. We talked about this in 8A as well. So during the next year, you're going to take the previous amount was 12,000, and again multiply it by 1.2 and keep going. So what we're going to do different here is instead of actually multiplying this out, we're just going to write 10,000 times 1.2. So take that and multiply by 1.2 again. When we multiply the same thing in a row, so 1.2 and 1.2 together, that is going to be 1.2 squared. So we really have 10,000 times 1.2 squared, which is 14,400. So we do it for another time. We're going to take our previous population, it's 10,000 times 1.2 squared, and we're going to have to multiply it again by 1.2. So now this is 1.2 cubed times 10,000, which is 17,280. So notice, so for linear, right, when we're adding the same thing each time, let's say we add 5, add 5, add 5, and so on, you would be adding 5 times 3. Right? So 5 3 times. For linear, for exponential, you're multiplying the same thing. So you'd be like multiplying like 1.2 times 1.2 times 1.2 and so on. And when you, so additional or multiple multiplications becomes, multiple additions become multiplication, multiple multiplications become a power. And notice that 3 years, you have a 3 in the exponent, 2 years you have a 2, 1 year you can say that there is a 1 here. So this is our pattern. We have the population after t years, it's going to be your initial population times 1.2 to the t. And here we just have the graph of that. So you have your initial population 14,400, and it's going to increase exponentially. Okay, so we briefly saw this in 8A, but here it is again, our formula for exponential functions. We have q equals q naught times 1 plus r to the t. So q, just like our y, is going to be our dependent variable. Right, so whatever we're measuring here. Q naught is going to be our initial amount of your dependent variable. When your t is 0, you're dependent, right? So t, of course, is your dependent variable. Or independent, sorry. Independent variable. Which is often in time, which is why we're going to use t. So r is going to be your rate of change. As a decimal. Positive means it's a growth. Negative means it's going to be decay, just like it was before. The only difference here between the linear and exponential is that here we're putting our exponent or putting our variable in the exponent rather than multiplying it. And our rate, of course, we have to change from a percentage to a decimal. Okay, so just also a little side note that the units of time for t and r must be the same. Of course, this is also true for your linear. Your time units for m and x also have to be the same units. If you're going to look at years for your rate, you have to look at years for your variable. The same thing here. So example 1. population of a town with initial population of 60,000 grows at a rate of 2.5% per year. Okay, so just like before, we have two values we have to find. The Q and the T are always going to stay in there, but we have to figure out what our Q naught and our R is. So Q naught, our initial one. Notice I say, there's a couple different ways to say this. I call it Q naught. Like naught is K-N-O-T. And I'm not really sure exactly where that comes from, but that's what it is. You can also say cube sub 0, because this is saying it is the dependent variable at time 0. I just call it Q naught, because that's how I learned it. Okay, so Q naught is the initial. So here we have the initial population of 60,000. Again, I didn't start with the identifying variables, which I should do. So let's do that. So we have the population grows at a rate of 2.5% per year. So knowing a little bit of English, where you can kind of take out this of 60,000 to kind of see where the subject and the verbs all kind of meet up. So the population grows at 2.5% per year. So just like with the slope before, the dependent comes first. So the population would be your dependent, and number of years would be your independent. In this case, it would be the number of years after today, or after that initial time period where it's 60,000. So it's your initial population is 60,000. Now your R, it's growing, which means it's going to be positive at a rate of 2.5%. So 2.5% as a decimal is 0.025. Okay, so when we plug it into our equation, we have Q naught is 60,000. It's going to be times 1 plus 0.025. And that's going to be raised to the T. Notice this is including our, changing from increasing to our percent of. So this does that work for us here. And then we're going to simplify this. So we're actually going to add this together, and that's going to be 1.025 to the T. Now if you can go straight here, you have 60,000 times your the percentage of to the T, then go ahead and do that. Otherwise, if you want to remember the 1 plus or minus R, you could do that here too. Okay, part B, create a table showing the value of the quantity Q for the first 10 years of growth or decay. Okay, so year 0, of course 60,000, that's today. After 1 year, it's going to increase by 1.025%. So what I'm going to do is I'm going to plug in 1 for T. So this is going to be 60,000 times 1.025 to the first. So I can type that in here. 60,000 times 1.025 to the first. So I get 61,500. From here, you can do the same thing we did in the previous sections before we had the formula. You could just take this and multiply it again by 1.025 each and every time. So you can say times 1.025, enter, and keep going all the way down. Or you can use the formula since we have it. So for year 2, you would say 60,000 times 1.025 squared. So 60,000 times 1.025 squared. We get 63,037, but if we round to the nearest whole like they ask us to do, that would be 63,038. And then what I can do, instead of typing this all in again, if I hit just the right arrow, I go all the way down to the end, and I can just rewrite that exponent. So now I'm going to put in a 3 for the next one. So I have 64, 613. Do the same thing. I'm going to go down to the end and change this to a 4. Get 66 to 29. And I would keep doing that, but for time's sake, I'm just going to write them down here. Okay. Okay, and then let's graph this. Now in MyMathLab, you're not going to actually have to graph these. You'll just have to be able to recognize them. But for our notes, we'll go ahead and graph it by hand. Okay, so at year 0, 5, 4, 3, 2, 1, 0. So 0 should be here. Just double checking. We have 60,000 here. At year 1, we have 63,000. So each of these are 5, 60, 65, 70, 75, 80, 85. So this is 65,000. So at year 1, we're not quite all the way to 65. Wait, no, we're at 61. Sorry. At year 1, it's 61,500. So it's just a little above 6,000. At year 2, we're at 63,000. Year 3, we're at 64. Year 4, we're at 66. Year 5, we're at 67. Year 6, we're almost at 70. Year 7, we're just over 70. And then 73. 74. And then 76. So we're not looking at a whole lot of years and at really big numbers, but there is a little bit of a curve here. So when you're looking at graphs in MyMathLab to figure out which one is right, the ones you're going to look at, how is it curved? Is it curving up or curving down? So it's either going to be curving up like this, or it's going to be curving down like that. So this, like right, if we're reading left to right, this is going to be increasing. So this is a growth. This one you start high and you're going low, so this is a decay. In order to figure that out, you're going to try to figure out whether the R is positive or negative. So if this is over 100%, then it's going to be growth. If it's less than 100%, it's going to be decay. But you'll also have words in your word problem saying it's either growing or increasing, decreasing, words up here that can tell you whether it's growth or decay. So you want to know whether it's up or down, and then you want to look at the start and end points. The first one, when t is 0, is usually easiest because they'll tell that to you. So here at 60,000, you want to make sure that it starts at 60,000. And then you're going to look at the end and make sure it ends about the right spots. This ends at 76. So 65, 70, 75, so it should be a little bit above that, and it is. Okay, so those are the two things that you really need to look at when you're trying to match up your graphs in MyMathLab. Okay, example 2. Now consider the following case of exponential growth. So a privately owned forest that had 1 million acres of old growth is being clear-cut at a rate of 7% per year. Create an exponential function. Okay, so figuring out our independent and dependent variables, we see that we have acres of old growth is being cut at a rate of 7% per year. So the number of acres is going to be my dependent, because it's mentioned first, that this is what's changing at a rate of 7% per year. So the number of years then is going to be my independent. Okay, so Q naught, that is going to be the initial number of acres. We're saying right now it starts off with 1 million acres. which as a number is 1 million. Okay, so my rate. Okay, so first I need to decide, is it increasing or is it decreasing? Well, here we're saying the number of acres is being clear cut. So clear cut means it's being cut down, which means the amount of growth that's there is going to be decreasing. So it's going to be a negative rate at 7.7%, so negative 0.07. So our equation is going to be Q equals Q naught, so 1 million times 1 minus 0.07 to the T. And then if we simplify that, it becomes 1 million times 0.93 to the T. So 1 minus 0.07 is 0.93. And this is what my math lab is going to want. This is a simplified version. Okay, now we fill in the table here. Again, we can just put in a 1 for, we put in whatever this T is in for T here. So we'd have 1 million times 0.93 to the first, which is 930,000. And then it would be 1 million times 0.93 to the second, which gives us 864,900, and so on. And we get 804. And these are all rounded to the nearest whole because that's what they ask us to do. Okay, I do recommend as you're watching this video to practice putting all this in your calculator. If nothing else, it'll help you get muscle memory and help you remember steps a little bit easier the more you do it. Okay. So those are my acres. Now graphing this. So remember last time we had a growth, this one is going to be a decay. So at 0 years, we're up to 1 million acres. At 1 year, it's 930, so this is, each of these are 10,000. So this is, actually this is a typo here, I forgot to change it, this should be 500,000. 600, 700, 800, 900, yeah, so this is 900,000. So at 1 year, we're at 930, so that's about right there. And then 864, that's about right there, 804. 748, about 750 here, 695, 646, 601, 559, 520, 483. So again, we see there's a slight curve here. You'd see it a lot better if it wasn't hand drawn. You see here it is decreasing. So you would want to find the one that decreases, one that starts at 0, 1 million, and then ends at 10, about, 483. And there will be a noticeable difference. Okay. Example 3. Answer the questions for the problem. Okay, so the average price of a home in a town was $175,000 in 2013, but home prices are rising by 5% per year. Okay, so it's rising by 5%, so it is indeed an exponential problem. And it's saying home prices are what's rising. So home prices are going to be my dependent variable. And it's per year, so the number of years is going to be my independent. Which means my Q naught is going to be my initial home price. So that is going to be the price now. So the town, the average price now is in 2013, I should say, 175,000. So that means T equals 0 is going to be the same as 2013, which means T is going to be the number of years after 2013. So our initial would be 2013, so 2014 would then be 1 year after, 2015 would be 2 years after, and so on. So we see down here 1 year after would be 2014, because this is 2013. So this would be 2015, this is 2016, 2017, and 2018. Okay, go back to the equation here. So Q naught is 175,000. So we need our rate. And here we're rising, which means it's going to be positive by 5%, so 0.05. So we're going to have 175,000, which is our Q naught, times 1 plus 0.05 to the T. Simplifying that gives me 175,000 times 1.05 to the T. Okay, so now we want to know the value of the average price of a home for the following 5 years. So from 2013 in the next 5 years. So again, we're going to put this number into our exponent. So this would be 175,000 times 1.05 to the first, which gives you 183,750. And then you do 175,000 times 1.05 squared, and you get 192,938, rounded to the nearest dollar. And then you do the same thing, you do 175, this time you put a cubed here instead of T, and so you get 202,584, then you put a 4 in the exponent and you get 212,714, and put a 5 in the exponent and you get 223,349. So it starts off at 175,000. 5 years later, it should be at $223,349. And then last example. Let's say we have a starting salary at a new job, it's $2,000 a month. At the end of each year, the monthly salary increases 5%. So again, you have 5%. So that is exponential. Now this one's worded a little bit differently. So this says at the end of each year, your monthly salary increases. So it's the word in front of the increases is your dependent, because the salary is what increases. So because the salary increases, that is your dependent. And it increases at the end of each year. So this each year is going to be my independent. Okay, and this one doesn't have a specific date, so it's just the years from year starting. So Q naught is going to be your initial salary, because that's your dependent. So initial salary at a new job is $2,000 per month. So we have $2,000 per month. So that is my monthly salary. So here dependent is monthly salary. So this is monthly salary per month. So Q naught is 2,000. So our rate, it increases, which means it's going to be positive R, and 5% is 0.05. So our equation is going to be 2,000 times 1 plus 0.05 to the T. Simplifying that is 2,000 times 1.05 to the T. Okay, now filling in this table, again we're going to do the same thing. We want to put in 1 for our exponent. So we have 2,000 times 1.05 to the first. And we get 2,100. Again, we're rounding to the nearest whole number, the nearest dollar. So now we want to put 2 in the exponent, so we do 2,000 times 1.05 squared, and we get 2,205. Then we put 3 in the exponent, and we get 2,315. And continuing on, this would be to the 4th, to the 5th, to the 6th, to the 7th, to the 8th, to the 9th, and to the 10th. Okay. Now if we were to graph this, 0 is 2,000, so each of these is 300, so 3, 6, 9, 12, 15, 18, 21. So 2,000 would be 19, 20, so it's about right there. Left 1 year is 2,100. That's right here. And then 2,205. It's about a third of the way up here. And then 2,315. 2,431. 2,553. 2,680. 2,841. 2,955. 3,103. And 32.8, something like that. So we have our curve here. Okay, now I didn't ask it, but you do need to kind of look and see, okay, is this reasonable? Like, can we actually use this to determine her salary at a between years? And technically, no. Right, so this is really only valid at the endpoints, at these points here. If I wanted to find her salary at year 4.5, it would actually still be the salary at year 4, right? But as long as you're looking at a full year amount, then this model will work. Okay, well that is 9B.